3 p.m. in Beijing. And it's a great honor of mine to introduce our today's speaker, Kim Seongjeong. He is going to tell us about links in SG times S1. Actually, Kim Seongjeong is proud of our seminar, and this talk is going to be a part of a very large mosaics when we try to show that if we have some non-trivial homology, actually in this case, non-trivial homology means something coming from S1, then we can create many tricks and many new constructions coming from knot theory. Well, in fact, concerning this talk, the most important thing is not SG, but I would better say that the most important thing is S1. In fact, the results Seongjeong is going to tell us about is on links in the cylinder, say S2 times S1 or D2 times S1. And actually, it's an attempt to apply techniques coming from virtual knot theory and other combinatorial things to the situation near the classical knot theory. So I'm very happy that Seongjeong is given a talk today. So please let us start.
Thank you. Thank you for introducing me. And can you hear me? Right, the sound is good. Can you hear me?
Yeah.
Oh, yeah. Thank you. Yes, today I'd like to talk about links in S times S1. This means a surface times S1. It means another other three-dimensional manifold and its lifting. The lifting means thanks to the S1, we can easily consider such a covering space. And if we have a knot in S times S1, then we can easily, we know there is a lifting. And today I'd like to discuss about the lifting from a knot in S times S1. But first of all, I'd like to tell about why I started to consider such a knot in the special three-dimensional manifold. And then firstly, we discussed how we study the knots in S times S1 combinatorically. It means how we define diagrams, how we define moves, and so on. And then we think about liftings and other one more. I think this I just tell you when I met this section. For the motivation, briefly, we remind some basic things. Firstly, the virtual links is an equivalence class of virtual knot diagram. So virtual knot diagram is a diagram with classical crossings and virtual crossing, modular generalized by the master moves, which described in this figure. It means virtual links, and the set of virtual links is a set of equivalent classes of virtual links diagram modulo these moves. But thanks by many mathematicians, for example, Kaufman and Kamada, and so on, we already know that virtual knot and link can be defined as circles inside the thickened surface. Thickened surface means SG times 0, 1. And two virtual links means two links in S times 01 are equivalent if one can be obtained from another by diffeomorphisms and stabilization and destabilization. Here, stabilization and destabilization means, roughly speaking, we add handles or remove handle. And this is the motivation why we started to consider the knots in S times S1. First, the 5-order link is in a S1, S3 is a collection of disjointly embedded circles such that its complement is diffeomorphic to the quotient of F times I by an equivalence relation. Here we can write so roughly speaking, we can say that J is a 5-order not if and only if its complement homeomorphic to times S1. Here, this is of a surface of J. And in 2013, Professor Mantroff and Christman tried to study virtual knots by using this this property of 5-order knots. A little bit more precisely, if we have a two component link in S3 and J is a 5-order knot, then we can say that K is inside the complement of J. Moreover, this is homeomorphic to sigma J times S1. And at first, we noticed it at the first of this talk. We can naturally we consider a covering which is defined by identity times exponential. Then, since K is a knot in sigma J times S1, in other words, K is a circle inside sigma J times S1, as we already know. There exists lifting to sigma J times R, especially if linking number of Kj is equal to 0, then K hat is a knot in sigma J times R. And Professor Christman and Mantroff proved that if K, K, J, and K prime, J prime are equivalent in S3. Then the obtained k hat and k hat prime are equivalent. Here notice that since k hat is inside the sigma j times r, and sigma j is actually a surface with boundary, this can be considered as a second surface. So we can say that k hat is a virtual knot, and so we can formulate this theorem as follow: if k j and k hat k prime j prime are equivalent in S3, then the obtained virtual knots are equivalent. But here, one very simple, very little problem is, if the linking number is not equal to 0, k hat is not, then k hat is not a knot in sigma j times r. So I had curious that, well, if linking number is not equal to 0, then in some sense we cannot obtain a virtual knot by lifting. But we already know that k is placed inside the good stream.
So here you always require that both G and G prime are fibered, no?
You're right. The J and J prime must be, yeah, fibered. Thank you. K is already placed in good three-dimensional manifold sigma j times S1. So, well, then maybe we can study this K without lifting. This K as a knot in surface times S1. So, so we are interested in the knots in S knots and links in S times S1 to study yeah, interested in links in S times S1. And we started to then to construct the way how to study S times S1. And the start of this research was the construct diagram, how we obtain diagrams from links in S times S1. Moreover, we needed to define the elementary things. What is the links in S times S1, and what is the equivalence relation for links in S times S1. So we start with this definition. A link in S times S1 is a smooth embedding of a disjoint union of S1 into S times S1. Here SG is the this is just analogous of the definition of link, classical link and virtual link. And in this figure, I try to describe the links in S times S1. Where since actually SG times S1 is quotient space of S times 0, 1. So firstly, we draw a box, which means S times 0, 1. And this upside and downside should be glued. So here, instead of gluing both sides, we draw simple curves outside the box like this. Then how? And then we define equalization as analogously with the definition of as in the case of virtual links. It means two links in S times S1 are equivalent if one can be obtained from another by diffeomorphisms on of S times S1 and stabilization and destabilization. And stabilization and destabilization also can be defined analogously as where I don't want to more precisely, but this means we add and remove handles on SG. Maybe you can say that after destabilization, we obtain SG minus 1, S1, and stabilization SG plus 1 times S1. And now we start how we define diagrams for links in S times S1. Actually, the idea is very simple. Let L be a link in S times S1. And since it is placed inside the S times S1, so we cut here and stretch it. Then without the outside, we obtain a kind of tangle inside this box. This box means S times 0, 1. And then we do projection onto the SG. Then we obtain such a diagram. Here, notice that there is a point on the upside and downside of this box. And those 2 points must be projected to the same point. And these 2 and these 2 also. So there we mark these points, which are from the points upside and downside, like this. And now we replace those points as a rules. Actually, in those points, as we already said, are from upside and downside, here and here. And then before we had like this. And we replace these points to the double line with different lengths as following rules. If the arc which is connected to the upside of this box should be connected to the longer line. And the arc which is connected to the downside of this box should connect it to the shorter line. Then by replacing those points to the double lines, we obtain such a diagram. And we call such diagrams a diagram for links in S times S1. Here we notice that this diagram actually placed on the SG. And by using elementary technique, we can show that for two links in SG times S1, the corresponding for two links in S times S1, their corresponding, they are equivalent if and only if their corresponding diagrams on SG are equivalent modulo those moves. Here, first three moves are just Reidemeister move. And but here, because of the double lines, we need to add such two moves. I'd like to how those moves are obtained. For the first move 4, let's think a link inside the S3 times S1. Locally looks like this. And here we say these are passing through here. Then the diagram must look like this. But here there are no other obstacles, so this arc can move like this. Then we obtain a diagram looks like this. So this force moves is needed. For move 5, obtained from this situation, a link in S times S1 locally looks like this. Then we obtain a diagram like this. But here we can notice that this arc can be moved to along this band. Then we obtain such link in S times S1. And from here, we obtain a diagram without double lines. So this move is needed, where analogously this also can. This move also needed. In other words, those two moves obtained because the arc can go through outside the box. But in virtual knot theory, we can think projection from the diagram onto the SG to the plane with virtual crossings. Then we obtain such diagrams from links in S times S1. And here we can say that we can prove that for things L and L prime, L and L prime equivalent in S times S1 if and only if their corresponding diagram on the plane are equivalent modulo the following moves. And here, except for those moves are actually from generalized Rademaster moves, and those moves are we already noticed. We already see the why they are needed. So thanks to this theorem, we can study the knots in S times S1 by using diagrams and a kind of Rademaster moves, as we already did in classical knot theory and virtual knot theory. And the next topic is degree of knots in S times S1. Actually, we changed the ambient space from S times 01 to S times S1. And we already see that because of this move, in some sense, over-under information is a little bit ruined, because this arc, when this arc passes through the double line, the over-under information is changed. But instead of that, we obtain very important and interesting information. How many times the knot rotates along S1. More precisely, in this section, we just considered a knot in S times S1. It means a circle as an embedded S1 in S times S1. And we several times said there exists a natural covering. Here, this is exponential actually. Then we can think such a commutative diagram of functions with second projections here. Then we can make simple Dix diagram like this: phi1 times k, phi2 compression k hat. And as we already studied in algebraic topology, if phi2 times k hat 0 is 0, then phi2 k hat 1 is in Z. And this integer we call this integer the degree of k. And geometrically, we know that this means how many times the circle rotates inside the S1.
Well, excuse me, I beg
Yeah.
your pardon. I would like to make one small remark. Actually, having lifted our knot to S1, our crossings, which were just bare crossings on the plane, obtain degrees. So these degrees are modular P, where P is the total degree. And actually having lots of new degrees, we can extract much more information than just from usual knot diagram. And actually we can get for free lots of invariants valued in pictures and free groups and many other objects. So this can be thought of as a very important tool, and actually not only for SG times S1, but also for the thickened cylinder, which appears more or less everywhere.
Yes, right. Thank you. Well, I want to show this situation a little bit more geometrically. For example, we have such a link in S times S1. Then it has a diagram, looks like this. Here we have two double lines. And its lifting looks like this. Because this link rotates along S1 twice. So if we correspond these points on the zero level plane, then it ends to the second level of plane in D times R. But here I'd like to note that actually degree of the degree of K can be calculated by using diagram of K in S times S1. It means here we have a diagram with orientation. And for each double lines, we give +1 or -1. If the orientation goes from the longer line to shorter line, or from shorter line to longer line, respectively. And in this case, we have +1 and +1. And by summing up all of these integers, we obtain 2, and actually this is equal to the degree of k. But if we end the to consider this information, then actually this is nothing, because well, we already know how we use this degree. Then in algebraic topology, and it just means how many times rotates the knot rotates along S1, and that's all. So I'd like to little bit more. I'd like to look this information a little bit more precisely. It means here we have the same link in S times S1, and here is lifting. Here notice that the outside of this box is nothing. This just presents the gluing of upside and downside. So it, in some sense, this is nothing. So you can say that this arc corresponding to the arc of lifting between d times 0 and d times 1. And here the blue line corresponds to the arc of lifting between d times 1 and d times 2. And in the level of diagram, this arc corresponds to the blue one. This arc corresponds to the 0 one. Since the 0 curve corresponding to the curve of lifting between d times 0 and d times 1, so we give 0 here. And since the blue line corresponds to the curve between d times 1 and d times 2, we give 1. And in usual case, if the arc corresponding to the curve between d times a and d times a plus 1, then when we give the integer value a to the curve, and we call this those integers the heights of
excuse me,
curve.
one more remark. It's much easier to get invariance of links than invariance of knots. For example, links have linking number. And this work is an attempt to create links from knots for free. And if we have links from knots for free, we have much more powerful invariance. So whenever we can extract a tiny bit of homology, we can get links, and we can get such things. Okay.
Thank you for the remark. And as we calculated degree of knots by using diagram, and this height also can be calculated by using diagram as follow. In this case, we say this is the base point, and the base point is on the double line. It is double line. Then the next arc we to the next arc we give 0, and then when we meet the double lines with plus 1, then the next arc will be labeled by a plus 1, and if we meet the double line with a minus 1, then we give label a minus 1. And by repeating this process till the we come back to the starting point. Then we can we can calculate heights for each axis. And for example, here we have a diagram of link in S times S1. And since the double lines have +1, +1, -1, -1, so its degree is equal to 0. And by if we think this is the base point for lifting, then we can label we can calculate the heights of each axis as follow. This is the 0, and since this have +1, the next arc will have +1. Since this is +1, so next one is 2, and here +1, since here -1, and come back to the starting point. And the next example, we have a link, a diagram of link in S time, not in S times S1 with degree 3, because this is +1, +1, and +1. And if we think this is the base point, then we can label this arc by 0, 1, 2, and we come back to the starting point. Here we notice that actually in our rule, when you come back here, the next arc should be 3, because this arc have +1, but this arc is already labeled by 0. Then to make sense our definition, they should be equal. So we say that this label, these heights are valued in Z3. So here we can remark that heights are valued in Cn. But the problem is, as we already noticed, the height can be changed where we fix the starting point. It means if we give start point and starting base point here, then we have different heights. But if we consider the differences on the at each crossings, then we can dots from this problem. More precisely, let the diagram is has for the diagram, each arc have heights, and we say that and for the classical crossing, the overall crossing have height B, and the under crossing have height A. And we define a label of this classical crossing by the differences of those heights. And then, since even if the height can be changed by moving base points, the differences is not changed, because every height together change it in +1 or -1. And by simple calculation, we can see that the labels satisfies those rules. If the classical crossing corresponding take part in the first Rademaster move, then the label should be 0. And if it corresponds to the crossings in Rademaster move 2, then they should be equal. And if 3 crossings are corresponding to the 3 points in Rademaster move 3, then it must satisfy this rule. Here, K is the crossing between the top arc and middle arc. And from this lemma, we can notice that if we give labels modulo 2, then the labels becomes a parity. But if we separate classical crossing by crossing with label 0 and others.
I think you should remain what the parity is.
Yes, parity means it's the mapping from C to G2 such that firstly, if C crossing in Rademaster move 1, then equal P C is equal to 0. If C1, C2 crossings in RM2, then P C1, P C2, 3, if C1, C2, C3 crossings in RM3, then P C1 plus P C2 plus P C3 is equal to 0. Here, since G2 is the ranges, the images in G2, so actually this is mode 2. And weak parities from third property, we can say that C1 or of P C1, P C2, P C3 equal to 0 or 1 just. Zero, but we permit to all of them equal to, excuse me. If we permit all of them equal to 1, then this is the weak parity. Actually, those relations and properties came from Gaussian parity, and the weak parities came from the projection from what from parity projection. But more precisely, please see the papers of Professor Mantel, which one is good for this to study parity. What's your which one is better good to study parity, you think?
Well, we can prove, for example, theorems about invariants which are valued in diagrams. For example, we can construct invariants such that they are valued not in numbers, not in polynomials, but in diagrams of the initial object, which can say a lot about all possible representatives. This is one thing. There is also a parity projection, which allows one, for example, to prove that, say, even objects form a subcategory of all objects, like classical knots embed into virtual knots, classical links embed into virtual links. We can prove lots of theorems like, for example, estimating, say, crossing number or other things just by looking at a graph, because a graph itself can be an invariant of everything. So having at least one Z2 valued parity, we can prove much more than just looking at, say, polynomial invariants or maybe group valued invariants.
And if you want to study more, see about the parity more precisely, then the book Virtual Knots, The State of Art by Professor Mantaram Lyutko, please see in this book. And anyway, our labels, if we restrict to G2, then we can obtain parity and weak parity as follow. But the next remark is actually the most important property of this label. Geometrically, the label of crossing C means how many times the curve from C to C turns around S1. It means for example, we have such link and not, maybe not, in S times S1. Then, for example, here we have a crossing. And we can see that the label means this information. We start from this crossing and it come back to itself after the knot turns around S1 3 times. And if we, 3 times. And actually, if we obtain this crossing on the plane, then its label must be to 3. And so, in some sense, we lose overall the information. But instead of that, we have a little bit more information by using S1, how many times the crossing turns around S1. And actually, this is very to understand why this is important, I need to mention such a keywords: the parity and homological parity, and the it's the which is related to those objects. But now I don't want to say more detailedly. But yeah, our labels are present this information, and moreover, we can know this information a little bit combinatorically. We don't need to find lifting of this link to S times S R to know this information, how many times it rotates along S1. And actually, this label have another geometric interpretation, but for that we need to refer the lifting of knots in S times S1. As we already referred at the first of this talk, if K is a knot in S times S1, there exists a lifting to S times R. Especially if K has degree 0, then its lifting become a knot again. And here in this section, I'd like to introduce how we obtain the lifting from the diagram of knot in S times S1. And this the algorithm I introduced with example. Here we have a knot in knot diagram of a knot in S times S1 of degree 0. And here each arc have heights with base point here. Then to obtain a diagram for knots in S of the lifting in S times R. Firstly, we draw 3 planes parallelly like this. Here, why 3? Because the arcs have heights 0, 1, 2, the 3 different heights. And then we draw for each plane the departure of arcs with degree 0 on the 0 plane, degree 1 on the 1 plane, and degree 2 on the 2 plane. And we connect them by as the following rule. We walk through here and here together. And when we meet the double line, and if it has +1, then we connect this to the arc on the next level. And here again, we obtain here and here we obtain we meet double line with -1, so we connect lower arc and lower arc. Then we obtain a kind of knot in S times R. And in this case, unfortunately, we obtain such a trivial knot in S times R. And by simple calculation, we can see that this algorithm works well. It means if we have two equivalent diagram, then the obtained diagram we call d hat and d hat prime are equivalent as knots in S times R or as virtual knots in. Well, this is just we check for each moves. Yeah. So, but please little bit focus on this example. Actually, when we lift the circle to the S times R by choosing different base points, we obtain different liftings. And in our cases, the base points are placed on the S times 0, and we constructed a lifting. But if we start from first level, then we obtain another diagram here, in this case, green one. And if we start from S3 times -1, then we obtain blue lifting. In this manner, we can obtain infinitely, we obtain a link with infinitely many components. But here, what is important? Here, notice that this crossing actually have label -2 because the height of overcrossing is 0 and height of undercrossing is 2. So 0 -2, 0 -2. And you can see that this crossing corresponds to this crossing between green one and blue one. And blue one was obtained with base point on the S times -1. And green one is obtained by choosing the base point on the S times 1. And the difference is 2. And yeah, it means actually the labels are, if the crossing has a label 2, then if we name each component of lifting 0, 1, -1, K2, and so on, such that the label agree to the level of base points, then the crossing with label -2 corresponding to the crossing of liftings between two components which have labels in difference 2. In this case, -1 and -1. Then we can expect that here we again obtain crossing. Yeah, and since this is equal to 0, then it must be K hat minus K hat 2. And here this corresponds to K hat -2. And so on.
So, but in the classical case, we get just a pile of knots one over the over the other. So this is nothing but just multiplication by piles. So for degree 0, so far we don't get, well, something which is not known to classical knot theory. For degree non-zero, it gives a lot.
Yeah. And this remarkable already I said. And as a corollary, we can show that where before we consider just one component and one lifting, but for two knots in S times S1 with degree 0, then the links which are obtained by infinitely many liftings are also equivalent in S times R, where it is not that it is obvious. But for the knots with degree K, by lifting, we cannot obtain a knot in S times R, but we can obtain a kind of long knots with infinitely many copies of a long knot.
I'm pretty sure that for some knots with whatever structure, for example, Legendrian knots, or if we have knots in some other, maybe in somewhere where we have some structure, vibration, or whatever else, we can get such a degree. So the simplest thing should be a Legendrian knot, so it should give rise to such non-trivial crossings and other things.
Yes. And if we change, if we consider the covering space, which is defined by I d times pi, such that pi g to k. If we consider such a covering, then even if k has non-zero degree, the lifting must be becomes a knot in S times S1 again. And analogously, we can obtain this lifting as follow. Where here we have a diagram of knots in S times S1 of degree 3. Then, as we did, we make planes depending on the number of heights, and we draw arcs on each planes. And then we connect them as we did. But for the arc on the height plane, since the degree is not equal to 0, we must connect this one to the lowest, the arc on the lowest plane. And in this case, we add double lines like this. Then we obtain a diagram of knot in S times S1 with degree +1 or -1. And analogously, we can show that this algorithm works well. And in this case, if we do lifting at each base points, then we obtain a link. But in this case, we just obtain a link with link of three components. Here, 3 obtained by degree, obtained from the degree of knots. And similarly, the label of crossings becomes mixed crossing between components with the numbering indifference, which is equal to the label. So, well, I think this till this week I can after this I can say that I can say why I think this important. This is important object, because for knots in S times S1, each crossing has labels from the information from S1, how many times it turns around S1 and come back to itself. And it works like parity, as we already remarked. But geometrically, it is not only represent how many times it turns around S1, but also it present a kind of mixed cross, geometrically present mixed crossing in the level of virtual knots, or the level of knots in S times S1 with degree +1 or -1. Moreover, why we expect this works better than parity? Because the parity has value in G2, but in this case the labels has in integer values, or even G3, G4, G5, and so on, which depending on the degree of K. So now I'm expecting to study. Moreover, the liftings are actually virtual knots or virtual links. Even we started from the knots in S times S1. So I'm expecting to study virtual knots by using more plentiful a kind of parity. And this section is just a section I'm working on. And briefly, I talk about these works, and I will end my talk. And the motivation is the following: where we considering knots or links in S times S1, and till now we think about the lifting to the SG times R or SG times S1 again. But the beginning of this work is from this one. If we have two component link forward knot, then K is inside the S times N J, which is homeomorphic to S3 times sigma J times S1. Yeah, this is not different homeomorphic. So I thought like that, where we know that from the two component link with a fibered knot, we can obtain a knot in S times S1. Then the reverse operation is possible. The reverse operation. It means is it possible to obtain two component link from a knot in SG times S1. Any question is this one? And here, firstly, we need to notice that the motivate at the beginning of this one is so I thought that if this diagram on the can be placed on the Seifert surface of fibered knot, where here the where is the important actually, but where then the corresponding classical link must give the original knots in SG times S1. So I tried to construct the following algorithm for the knot in S times S1, and this is the diagram of S times S1. And then we present then we just now we ignore the double lines, but we consider it as a virtual knot. Then in virtual knot theory, we can obtain the underlying surface by using band presentation. Let's follow it. And then for each double line, we little bit modify the bands as following rules. If we have the double line like this and the bands passing through here, and actually this have +1, then we link one part of the bands with our diagram to have link number 1. Means if can we do like this? In this case, it has link number 1. This case linking MBR is -1. Then from our diagram, we can obtain such a link diagram. Here, firstly, notice that the blue components is trivial knot actually, because it looks like this. And the linking number is equal to the degree of knot. Then it is obvious that another component, moreover, the Seifert surface of the blue components is actually equal to this band. It means our first purpose was that to make our original diagram to be placed on the gyroid surface of forward knot. But our new component, the blue component, is trivial, so it is forward. And by our algorithm, it is obvious that we obtain a gyroid surface, and our original diagram were placed on the gyroid surface. So, well, frankly speaking, then this gives our original not in S times S1 where, frankly speaking, I don't know. I'm trying to prove that, but I think where it must be. So the component J is forward link, yes, because it is nothing but trivial. But is this well defined? It means from the same diagrams of knots in S times S1, we obtain same link, classical link. But no, because here those two diagrams are equivalent in S3 times S1. But from our algorithm, we obtain different classical links. First one is just nothing but Hopf-link and trivial components. And second one is Borromean ring. So, well, there is not that good result for me, but in some sense, I had hope like this one. Here, we did crossing change by using double lines. But because of that, in some sense, this new red components is, how to say, linked with the other components. So in this manner, maybe we can study classical links also by using links in S times S1, but it is just my hope with a specific way. And actually, yeah, I already said on my further researches, and that's all of my talk. Thank you very much for attention, and sorry for not well arranged talk.
In my opinion, it was quite well arranged. Thank you very much for a very deep talk with lots of new ideas. Dear colleagues, please ask your questions, give your remarks and comments. Please unmute your microphones if you wish, or write on the chat line. I left some comments on the chat line, so you can start answering them. Well, I have one more question, so possibly maybe this is a hope. We can do lots of similar things when we are when we have something of codimension 2. For example, I'm pretty sure that we can analyze, for example, complex codimension 1 surfaces. There was some step towards it in our joint work with Jayan. So if we have something of codimension 2, then well, we can do similar things.
Frankly speaking, for me, that the work of you with Jian is not known. I don't know where. So yeah, if I just need to study your works, and I will think about that. Thank you. One question. Yes. Instead of wrapping as using the lifting to acquire, could you get anything interesting by unwrapping the The disk. First of all, thank you for your question, good question. And my answer is I don't know, but I have such a not proved answer. Actually, the parity came from the SG. It means virtual knots on the SG times 0, 1, and many parity properties came from the homological information of SG. And yeah, so maybe from this fact, you can find your answer. One can find the answer on your question, but I'm sure that, but I didn't thought about this. So yeah, that's my answer. Sorry.
Okay, thank you very much. Are there any further questions? Okay, I wish all of you Happy New Year. 祝大家春节好. And I think this is all for so there is some comment.
Yes. How about other mapping topology? Frankly speaking, I don't know, but it might be interesting, but I don't know. Mapping topology. Sorry, I cannot give you an answer, but thank you for questions.
Okay,
Yeah.
Thank you very much for coming to the talk. So I wish everyone happy
New Year.
Chinese Easter New Year.
Chinese New Year.
Chinese New Year.
新年快乐。